Look up at the night sky. What do you see? Distant points of light, scattered across the velvet darkness like diamonds on black silk. But what you're really seeing is time itself, light that left those stars thousands, millions, even billions of years ago, finally reaching your eyes in this singular moment. Right now, as you watch this, you are standing on a rock hurtling through space at 67,000 miles per hour. This rock, our Earth, is orbiting a medium-sized star we call the Sun, which itself is racing around the center of our galaxy at 500,000 miles per hour. Our galaxy, the Milky Way, contains 200 billion stars, and it's just one galaxy among 2 trillion others in the observable universe. The scale is incomprehensible. If you could travel at the speed of light, 186,000 miles per second, it would take you 100,000 years just to cross our galaxy. To reach the edge of the observable universe would require 46 billion years of travel. The numbers become meaningless. The distances, absurd. And yet, here we are. On this insignificant speck of cosmic dust, something impossible happened. Matter became aware of itself. Atoms forged in the hearts of dying stars arranged themselves into patterns complex enough to contemplate their own existence. We look out at the universe, and the universe looks back at itself through our eyes. But here's the unsettling truth, the cosmic puzzle that keeps physicists awake at night. We shouldn't exist. Not even close. The odds against our existence are so astronomical, so preposterously small, that every rational calculation suggests we should be looking at an empty, lifeless void. The universe, you see, is balanced on a knife's edge. 6 numbers, 6 fundamental constants woven into the very fabric of reality, determine everything. The strength of gravity, the efficiency of nuclear fusion, the density of the cosmos, the energy of empty space itself. These numbers are not arbitrary. They are precise, exact. And if any one of them were even slightly different, changed by the smallest fraction of a percent, stars wouldn't form. Atoms wouldn't bond. Chemistry wouldn't work. Life, in any conceivable form, would be impossible. Think about that for a moment. 6 numbers. Not 7. Not 100. Just 6 specific values that had to be exactly what they are for you to be here, watching this, thinking these thoughts. The astronomer Martin Rees called them just 6 numbers. Others have called them evidence of design, proof of a cosmic blueprint, the fingerprints of God in the machinery of creation. But labels don't matter. What matters is the staggering reality they represent. Our universe is fine-tuned for existence with a precision that defies comprehension. Imagine rolling dice in the void before creation. The chances of getting our universe, a universe capable of producing stars, planets, and consciousness, are incomprehensibly small. 1 in 10 to the power of 100. 1 in a googol. Numbers so large they have no practical meaning. You might as well say, impossible. And yet, the impossible happened. Against odds that should have consigned us to eternal non-existence, here we stand. Thinking, feeling, loving, creating, questioning our own unlikely presence in this vast cosmic arena. So tonight, we're going to take a journey through the 6 numbers that built our reality. We're going to understand why each one is necessary, what would happen if they were different, and why their precise values represent perhaps the deepest mystery in all of science. We'll explore the strength that holds galaxies together while remaining weak enough to allow stars to shine. We'll witness the nuclear ballet that transforms hydrogen into the elements of life. We'll see how the density of the universe determines its ultimate fate. We'll confront the mysterious energy that's tearing space itself apart. We'll watch the quantum seeds that grew into galaxies. And we'll discover why we exist in precisely 3 dimensions of space. Not 2, not 4, but exactly 3. By the end of this journey, you'll understand something profound. You are not just in the universe. You are a part of it. The atoms in your body were forged in the nuclear furnaces of stars that died billions of years ago. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was created in stellar explosions so violent they outshone entire galaxies. You are, quite literally, made of stardust. And the fact that those atoms can arrange themselves into something as complex as a human being, something that can look back at the stars that made it and understand the journey, is perhaps the most remarkable fact in all of existence. But before we dive into the numbers themselves, we need to understand what we mean by fine-tuning. We're not talking about religious belief or philosophical preference. We're talking about cold, hard physics. Measurable quantities. Numbers you can test in laboratories and observe through telescopes. These 6 numbers are not human inventions. We didn't choose them. We discovered them. They were waiting here, embedded in the structure of reality itself, long before the first human ever looked up at the stars and wondered, why? Our ancestors saw the cosmos and created myths to explain it. They invented gods and spirits, wove stories of creation and destruction. But they were asking the right question. Why is there something rather than nothing? Why does the universe have the particular character that it does? Today we have better tools. We can peer back to the first moments after the Big Bang. We can weigh entire galaxies. We can measure the expansion rate of the universe to extraordinary precision. And what we've discovered is more mysterious than any ancient myth. The universe appears to have been expecting us. This is the echo of creation itself, the cosmic microwave background radiation. It's the oldest light in the universe, released when the cosmos was just 380,000 years old, a mere infant compared to its current age of 13.8 billion years. And encoded in the tiny fluctuations in this ancient light are the seeds of everything that would come after: galaxies, stars, planets, life, consciousness. But those seeds could only grow in a universe with precisely the right properties. Change any of the 6 numbers we're about to explore, and you get a stillborn cosmos, a universe that flashes into existence and immediately collapses, or expands so rapidly that no structures ever form, or produces only hydrogen with no possibility of complex chemistry. So as we prepare to explore these 6 numbers in detail, hold this thought in your mind. You are watching this because the universe won the lottery. 6 cosmic dice rolled before time began, and somehow, impossibly, they all came up exactly right. The question is, was it luck? Necessity? Design? Or something stranger still, something our current understanding of physics can barely begin to grasp? Let's find out. Our journey begins with the weakest force in the universe. And that weakness? It's the only reason you exist. Gravity. The force that keeps your feet on the ground, that holds the moon in orbit around Earth, that binds galaxies together across cosmic distances. It feels strong when you stumble and fall, or when you try to jump high and gravity pulls you inevitably back down. But here's the shocking truth. Gravity is pathetically, absurdly, ridiculously weak. So weak that we can measure its feebleness with a simple experiment you can do right now. Take a refrigerator magnet, a piece of metal smaller than your thumb. Now use it to pick up a paperclip. Congratulations! You just watched a tiny magnet overpower the gravitational pull of the entire Earth. That paperclip is being pulled down by the gravity of a planet weighing 6 trillion kilograms, and a magnet the size of your thumb beats it effortlessly. This is N, the ratio of the electromagnetic force to gravitational force. Its value is approximately 10 to the 36th power. That's a 1 followed by 36 zeros. It means that electromagnetic forces are 1,000,000,000,000,000,000,000,000 times stronger than gravity. And here's the profound mystery. If gravity were any stronger, if n were smaller, the universe would be a very different place. And by different, I mean utterly hostile to life. Imagine turning up gravity's strength. Just a little bit. Maybe make it 1,000 times stronger. That sounds reasonable, right? It would still be vastly weaker than electromagnetism. But watch what happens to stars. In our universe, stars are vast nuclear furnaces that burn steadily for billions of years. Our sun has been shining for 4.6 billion years and will continue for another 5 billion. This longevity is crucial. It gives life time to emerge, evolve, and develop complexity. But increase gravity's strength, and stars become small, hot, and short-lived. With gravity 1,000 times stronger, stars would be 1,000 times smaller. And their lifetimes? They'd burn out not in billions of years, but in millions. Maybe just thousands. Do you see the problem? Complex life took 4 billion years to evolve on Earth. 4 billion years of gradual change, mutation, selection, and refinement. In a high-gravity universe, the stars would burn out before life had a chance to begin. But it gets worse. Increase gravity enough, and stars can't form at all in the way we need them to. They collapse too quickly, burning through their fuel in stellar catastrophes rather than the slow, steady fusion that powers our sun. And planets? Forget about it. In a universe with stronger gravity, planets would be crushed under their own weight. The surface gravity would be so intense that no life form could possibly stand or move. Evolution would have no room to experiment with complex body plans. But here's the flip side. What if gravity were weaker? What if we made an even larger? At first, it seems less catastrophic. Weaker gravity means stars burn more slowly, last even longer. That sounds good for life, right? Wrong. Make gravity too weak, and stars never form in the first place. Gas clouds in space would never collapse under their own weight. The universe would remain a thin fog of hydrogen and helium, spreading ever thinner as space expands. No stars. No planets. No chemistry beyond the simplest elements. Gravity needs to be weak enough to allow structures to grow slowly, to give stars long, stable lives. But it needs to be strong enough to pull matter together in the first place, to light the nuclear fires that forge new elements. It's a Goldilocks situation. Too strong, and everything happens too fast. Too weak, and nothing happens at all. The value of n, that ratio of 1 to 10 to the 36th power, sits in the narrow range where cosmic evolution unfolds at just the right pace. But here's what should really blow your mind. There's no known physical reason why n has to be this particular value. In our current understanding of physics, gravity's strength is a free parameter, something that could, in principle, be anything. The laws of physics don't require it to be weak. They just describe that it is. Why is gravity so much weaker than the other forces? It's one of the deepest unsolved problems in physics, often called the hierarchy problem. Some theories suggest extra dimensions of space where gravity leaks away, diluting its strength in our three-dimensional slice of reality. Other theories propose that gravity is actually strong, but we perceive it as weak because of quantum effects. Martin Rees put it elegantly, in a high-gravity universe where n were only 10 to the 30 instead of 10 to the 36, stars would be 1 billion times less massive than the Sun and would burn 1 million times faster. A mini-sun would exhaust its energy in a year. There would be no time for evolution, even if planets could exist. Every carbon atom in your body was made in a star. Every oxygen molecule you breathe was forged in nuclear fusion. The iron in your blood was created in a supernova explosion. None of this would be possible if n had a different value. So the next time you feel gravity pulling you down, remember, you're feeling the weakest force in nature. And that weakness is the foundation of your existence. But gravity's fine-tuning is just the beginning. Our next number is even more precise, even more critical. Change it by less than 0.5%, and chemistry itself becomes impossible. Welcome to the heart of a star. The temperature here is 15 million degrees Celsius. The pressure is so intense that matter exists in states we can barely reproduce on Earth. And in this hellish environment, something miraculous is happening. Protons, the nuclei of hydrogen atoms, are being forced together. This shouldn't be possible. Protons are positively charged, and like charges repel. The electromagnetic force pushes them apart with tremendous energy. But in the core of a star, temperatures and pressures are so extreme that some protons overcome this repulsion and fuse together. When they do, something extraordinary happens. A tiny amount of mass, less than 1% of the original protons, converts directly into energy according to Einstein's famous equation, equals mc². This is nuclear fusion, the process that powers every star in the universe. And this number, epsilon, tells us exactly how efficient that conversion is. Its value is 0.007, or 0.7%. When 4 protons fuse to make one helium nucleus, 0.7% of the original mass becomes pure energy. That might not sound like much. Less than 1%? But that tiny efficiency is why the sun has been shining for 4.6 billion years and will continue to shine for another 5 billion. If fusion converted more mass to energy, stars would burn out faster. If it converted less, they might not shine at all. But the real miracle of epsilon isn't just that it allows stars to burn steadily. It's that this precise value, 0.007, is exactly what's needed to build the periodic table of elements. Let me explain. The universe began with hydrogen and helium, plus trace amounts of lithium. That's it. The Big Bang created the 3 simplest elements and then stopped. To make everything else, carbon, oxygen, nitrogen, iron, gold, uranium, you need stars. Stars are element factories. In their cores, they fuse hydrogen into helium. Then, as they age and their cores get hotter, they fuse helium into carbon and oxygen. Massive stars keep going, creating neon, magnesium, silicon, all the way up to iron. This is nucleosynthesis, the creation of atomic nuclei. And every single element in your body except hydrogen was made this way. You are quite literally built from the ashes of dead stars. But here's the catch. This entire process depends on epsilon having exactly the right value. Change it by just a tiny amount, and the chemistry of the cosmos falls apart. Imagine if epsilon were slightly smaller, say 0.006 instead of 0.007. A reduction of just 14%. With a smaller epsilon, nuclear fusion would be less efficient. Stars would have to be hotter and denser to sustain fusion reactions. They'd burn their fuel differently, and crucially, they'd have a much harder time building elements heavier than helium. In fact, if epsilon were too small, stars might never produce carbon or oxygen at all. They'd burn through their hydrogen, convert it to helium, and then nothing. The universe would be stuck with just the 2 simplest elements. No carbon means no organic chemistry. No oxygen means no water. No water means no life as we know it. But the opposite scenario is even more catastrophic. What if epsilon were larger? Say 0.008, just a 14% increase. With a higher epsilon, fusion would be more efficient. More mass would convert to energy with each reaction. At first, this might sound good. More energy means brighter stars, right? Wrong. More efficient fusion means stars burn out faster. But that's not the worst problem. The real disaster is this. If epsilon were too large, the early universe would have been catastrophically different. In the first 3 minutes after the Big Bang, the universe was hot enough and dense enough for nuclear fusion to occur everywhere, not just in stars. This primordial nucleosynthesis created the hydrogen and helium that filled the early cosmos. But if epsilon were larger, if fusion were more efficient, something terrible would have happened. The Big Bang would have converted not just some hydrogen into helium, but all of it. Or worse, it would have kept going, fusing everything into heavy elements immediately. Imagine a universe with no hydrogen. Hydrogen is the simplest element, the most common element, the fuel that powers stars. Without it, stars can't form. Without stars, you don't get the slow, gradual creation of heavy elements over billions of years. You don't get planets. You don't get chemistry. Alternatively, if the early universe had been too efficient at fusion, everything might have fused into iron, the most stable nucleus. And iron doesn't fuse. When you try to fuse iron, it absorbs energy instead of releasing it. Iron is where fusion stops, where stars die. So if the universe had started with mostly iron, there would be no fuel for stars. No nuclear reactions. No energy source. Just cold, dark matter drifting through expanding space. But epsilon is 0.007. Not 0.006. Not 0.008. Exactly right to allow the Big Bang to create hydrogen and helium, and then allow stars to slowly convert that hydrogen into all the heavier elements necessary for life. This precision was first recognized by the astronomer Fred Hoyle in the 1950s. Hoyle was studying how carbon is made in stars, and he realized there was a problem. To make carbon, you need to fuse 3 helium nuclei together. But this is incredibly difficult. The chances of 3 helium nuclei colliding simultaneously are vanishingly small. The physics suggested that stars should barely produce any carbon at all. And yet, carbon exists. We're made of it. The Earth is full of it. Hoyle realized there must be a resonance, a special energy level in the carbon nucleus that makes the triple helium fusion much more likely. He predicted this resonance should exist at a very specific energy level. And when experimentalists looked, there it was. The resonance existed, exactly where Hoyle predicted. This is now called the Hoyle state, and it's the reason stars can make carbon efficiently. But here's the kicker. The Hoyle state sits at an energy level that's exquisitely sensitive to the fundamental constants of physics, including epsilon. Change epsilon by a small amount and the resonance shifts. The carbon-12 nucleus no longer has a convenient doorway for helium nuclei to enter. Fred Hoyle himself was so astounded by this fine-tuning that he later wrote, "A common-sense interpretation of the facts suggests that a superintellect has monkeyed with physics as well as with chemistry and biology. The numbers one calculates from the facts seem to me so overwhelming as to put this conclusion almost beyond question." This from a man who was a staunch atheist for most of his life. The precision of epsilon shook even his convictions. So every breath you take, every carbon atom in your body, every living thing on Earth, all of it exists because epsilon is 0.007. Make it 0.006, and the cosmos is starved of heavy elements. Make it 0.008, and the Big Bang burns all the hydrogen, leaving no fuel for stars. The margin for error is breathtakingly small. A change of 0.5% in either direction, and the universe becomes sterile. No chemistry, no complexity, no life, no consciousness, no one to wonder why. You are holding stardust. Carbon forged in the heart of a dying star, expelled in a supernova, drifting through space for eons, eventually coalescing into a planet, and finally arranging itself into a form that can think and feel and wonder about its own origins. And all of it hinges on a number, 0.007. Zoom out. Further. Keep going. Out past our solar system, past the Milky Way, past our local group of galaxies, past the superclusters, until you can see the large-scale structure of the cosmos itself. But focus not on the pattern, but on what's between the galaxies. Vast amounts of it. And that space is not static, it's expanding. Every second, every galaxy not bound to us by gravity is getting farther away. This is the expansion of the universe, discovered by Edwin Hubble in 1929. It's one of the most profound discoveries in the history of science. The cosmos is not fixed and eternal, but dynamic and evolving. And if you run the expansion backward in time, everything converges to a single point 13.8 billion years ago, the Big Bang. But here's the question that haunted astronomers for decades. Will the expansion continue forever? Or will gravity eventually slow it down, halt it, and reverse it, causing the universe to collapse back into a big crunch? The answer depends on a number called omega, the cosmic density parameter. Omega is the ratio of the actual density of the universe to the critical density, the exact amount of matter and energy needed to balance the expansion against gravity's pull. If omega is greater than 1, the universe is closed. There's enough matter and energy that gravity will eventually win. The expansion will slow, stop, and reverse. In tens or hundreds of billions of years, all the galaxies will rush back together in a catastrophic big crunch. If omega is less than 1, the universe is open. There's not enough matter to stop the expansion. Galaxies will drift apart forever, accelerating as they go, until the universe becomes a cold, dark, dilute fog. The stars will burn out one by one, and eventually, even black holes will evaporate via Hawking radiation. In 10 to the power of 100 years, the universe will reach heat death, maximum entropy, no usable energy, no structure, no change. But if omega is exactly 1, precisely balanced, the universe is flat. Expansion continues forever, but just barely. The rate slows down over time, approaching 0 but never quite stopping. This is the knife edge, the critical balance between the two extremes. So which is it? What's the value of omega? Decades of observations have given us an answer, and it's shocking. Omega is 1, or extremely close to it. Current measurements give omega equals 1.00 plus or minus 0.02. The universe is flat, or so close to flat that we can't measure the difference. It sits exactly on the critical density, balanced between eternal expansion and eventual collapse. Now, you might think, so what? It has to be some value, right? Why is 1 special? Here's why. In the early universe, omega didn't have to be close to 1. It could have been anything. But if it were significantly different from 1, even by a tiny amount, the consequences would have been catastrophic. Imagine omega is slightly larger than 1, say 1.01 instead of 1.00. Just a 1% difference. What happens? With slightly too much density, gravity is stronger. The universe expands after the Big Bang, but the expansion slows dramatically. Within a few 100,000 years, maybe a few million, gravity wins. The universe collapses back on itself in a big crunch. No time for stars to form. No time for galaxies. Certainly no time for life to evolve. The cosmos flashes into existence and immediately dies, snuffed out by its own gravity. Now imagine omega is slightly smaller than 1, say 0.99 instead of 1.00. Again, just a 1% difference. What happens? With slightly too little density, gravity is weaker. The universe expands rapidly, so rapidly that matter never has a chance to clump together. The tiny density fluctuations that should grow into galaxies are overwhelmed by the expansion. No galaxies form. No stars ignite. The universe becomes an ever-thinning fog of hydrogen and helium, spreading into the infinite void. Again, no possibility for life. So omega needs to be very close to 1. Close enough that the universe expands slowly enough for structures to form, but not so slowly that it collapses too quickly. 1 second after the Big Bang, omega must have been equal to 1 to within 1 part in 100 trillion. That's 1.0000000000000000000. 15 decimal places of precision. At the Planck time, the earliest moment we can meaningfully discuss, 10 to the power of negative 43 seconds after the beginning, omega had to be equal to 1 to within 1 part in 10 to the power of 60. That's a decimal point followed by 60 zeros, then a 1. There's no known physical reason why omega should start out so perfectly tuned. In our current understanding, the initial value of the cosmic density parameter is simply an initial condition, something that was set at the moment of the Big Bang for reasons we don't understand. Inflation is an elegant idea, and observational evidence supports it. But it doesn't eliminate the mystery, it just pushes it back 1 level. Why did inflation happen? What triggered it? What set its parameters? We've replaced one fine-tuned number with a fine-tuned mechanism. Regardless of the explanation, the consequence is clear. We live in a flat universe, or one so close to flat that 13 billion years of expansion haven't significantly changed it. And this flatness, this precise balance between expansion and gravity, is what allowed galaxies to form slowly, stars to ignite gradually, and life to eventually emerge. If omega were different by just 1% early on, you wouldn't be here. The universe would either have collapsed eons ago, or expanded so rapidly that matter never condensed into structures. No galaxies. No stars. No planets. No you. The cosmic density parameter is the third number that shouldn't have the value it does. But it does. And because it does, the universe has had time to create complexity, to build galaxies, to forge elements in stars, to give rise to worlds where matter can contemplate its own existence. But our journey isn't over. In fact, we're about to encounter something even stranger. Because there's another form of energy in the universe, one that's not matter at all. It's the energy of empty space itself. And it's tearing the cosmos apart. Look at this. Nothing. Empty space. A vacuum. You might think there's nothing here. No matter, no energy, no anything. You'd be wrong. Empty space is not empty. At the quantum level, it seethes with activity. Particles and antiparticles pop into existence for the briefest instant, then annihilate each other and disappear. Energy fluctuates wildly at scales smaller than atoms. The vacuum itself has energy. This is the zero-point energy of the quantum vacuum. And it has a consequence that's literally cosmic in scale. It causes space itself to expand. This is dark energy, a mysterious force that fills all of space uniformly and pushes the universe apart. And its strength is measured by a number called lambda. Lambda, the cosmological constant. Lambda represents the energy density of the vacuum. It's the fourth of our 6 numbers, and it's perhaps the most mysterious of all. Because lambda's value is, well, it's weird. In the natural units that physicists use, Planck units, lambda has a value of about 10 to the power of negative 120. That's a decimal point, followed by 119 zeros, then a 1. It's mind-bogglingly small. But here's the puzzle. Quantum field theory, our best theory of how particles and forces work, predicts that lambda should be huge. Not small. Huge. About 10 to the power of 120 in those same units. A 1 followed by 120 zeros. The difference between prediction and observation is a factor of 10 to the power of 240, 1 with 240 zeros after it. This is called the cosmological constant problem, and it's the worst prediction in the history of physics. We're not off by a little bit. We're off by more than 100 orders of magnitude. Nobody knows why lambda is so small. And nobody knows why it has the specific tiny value that it does. But what we do know is this. If lambda were much larger, the universe would be a very different place. Imagine increasing lambda by a factor of 10. Just 10 times larger, still incredibly small compared to what theory predicts. What happens? The universe expands faster. Dark energy pushes space apart more vigorously. And crucially, this happens not just today, but throughout cosmic history. In the early universe, when galaxies were trying to form, the accelerated expansion would have torn apart the density fluctuations before they could collapse into structures. Increase lambda by a factor of 100, and the problem is even worse. The universe expands so rapidly that atoms themselves might not hold together. Molecules certainly wouldn't. Chemistry becomes impossible. But what about decreasing lambda? What if the cosmological constant were smaller, or even negative? A negative lambda would mean that empty space has negative pressure. It would pull the universe together instead of pushing it apart. This would enhance the effect of gravity, causing the universe to collapse much sooner. Depending on how negative lambda is, the universe might collapse in just a few billion years, not enough time for life to evolve. Or it might collapse so quickly that stars and galaxies never form at all. So lambda needs to be positive, but just barely. Large enough that the universe doesn't collapse, but small enough that galaxies have time to form before the expansion accelerates too much. And our universe sits right in that narrow range. Lambda is positive but extraordinarily small. So small that dark energy only started to dominate the universe's expansion about 5 billion years ago. For the first 8 or 9 billion years of cosmic history, matter and gravity were in control. Galaxies formed, stars ignited, heavy elements were forged. Our solar system came into being 4.6 billion years ago. Life emerged on Earth. Evolution had time to work its slow magic. But now, in the current epoch, dark energy is taking over. The expansion of the universe is accelerating. Distant galaxies are moving away from us faster and faster. In the far future, trillions of years from now, the universe will expand so rapidly that even nearby galaxies will disappear beyond our cosmic horizon. But we're here now in the brief window between too early for complex life and too late for galaxies to stay together. We exist in the eye of the cosmic storm. This timing is sometimes called the cosmic coincidence problem. Why do we happen to exist at just the moment when matter and dark energy are roughly balanced? Why not earlier, when matter dominated? Why not later, when dark energy will rule absolutely? Some argue it's not a coincidence at all, it's observer selection bias. We can only exist during the era when galaxies and stars are possible. If we tried to exist in the far future, there would be no stars to forge elements. If we tried to exist in a universe with a larger lambda, no galaxies would have formed in the first place. But this explanation doesn't eliminate the mystery of why lambda has the absurdly small value that it does. Why not exactly 0? Why not larger or smaller by a factor of 2 or 10? Einstein himself struggled with lambda. When he first developed general relativity, he added the cosmological constant to his equations to allow for a static universe, He thought the cosmos was eternal and unchanging, so he needed a repulsive force to balance gravity. When Hubble discovered the expansion of the universe in 1929, Einstein called the cosmological constant his biggest blunder. If he'd trusted his original equations without the extra term, he could have predicted the expansion of the universe before it was observed. But decades later, when astronomers discovered that the expansion is accelerating, lambda came roaring back. It wasn't a blunder after all, it's a real feature of the universe. Empty space really does have energy, and that energy is determining the ultimate fate of the cosmos. In 1998, two teams of astronomers studying distant supernovae discovered that the universe's expansion is speeding up, not slowing down. This discovery earned the Nobel Prize and completely changed our understanding of cosmology. Today, we know that dark energy makes up about 68% of the total energy content of the universe. Dark matter accounts for 27%. Ordinary matter, the stuff we're made of, the stuff we can see, is just 5%. We live in a universe dominated by things we don't understand. Dark energy is the biggest component, and we have no idea what it really is. Is it truly a cosmological constant, the same everywhere and everywhen? Or is it something more exotic, a field that changes over time, or a sign that our theory of gravity needs modification? What we do know is that lambda's tiny value is what makes our existence possible. Make it larger and galaxies never form. Make it smaller or negative, and the universe might collapse too soon. The window for life is narrow, and we're in it. 4 numbers down. 2 to go. And the next one is written in the very structure of the cosmos, in the galaxies themselves. You're looking at baby picture of the universe. This is the cosmic microwave background radiation, light released when the cosmos was just 380,000 years old, a tiny infant compared to its current age of 13.8 billion years. Notice the pattern. It's not perfectly smooth. There are slightly hotter spots and slightly cooler spots. These temperature differences are tiny, just a few millionths of a degree. But they're incredibly important, because those tiny fluctuations are the seeds of everything that exists today. Every galaxy, every star cluster, every large-scale structure in the universe grew from these quantum ripples in the primordial plasma. This brings us to our 5th number, Q, the amplitude of these density fluctuations. Q measures how lumpy the early universe was, how much denser some regions were compared to others. Q is about 10 to the power of -5, or 1 part in 100,000. That means that in the early universe, the densest regions were only 0.001% denser than the average, and the least dense regions were 0.001% less dense. A tiny number, but it's perfectly calibrated. Too small, and those fluctuations would never grow into galaxies. Too large, and the universe would collapse into black holes everywhere. Let me explain how structure forms in the universe. After the Big Bang, matter was spread almost uniformly through space. Almost, but not quite. There were tiny quantum fluctuations, random variations in density caused by the uncertainty principle operating in the first moments of existence. Inflation, that exponential expansion in the first fraction of a second, stretched these quantum fluctuations to cosmic scales. Regions that were slightly denser stayed slightly denser. Regions that were slightly less dense stayed less dense. Then, as the universe expanded and cooled, gravity started to work on these density differences. Regions that were slightly denser had slightly stronger gravity. They attracted more matter. Over millions of years, they became noticeably denser. Over hundreds of millions of years, they became significantly denser. Eventually, when the density in these regions became high enough, hydrogen gas collapsed, heated up and ignited, forming the first stars. These stars clustered together, forming the first galaxies. Galaxies clustered together, forming groups and clusters and superclusters. All of this, all the structure in the universe, emerged from amplifying those initial fluctuations characterized by Q. And Q needs to be just right. If Q were smaller, say 10 to the power of -6 instead of 10 to the power of -5, the initial fluctuations would be 10 times weaker. With smaller fluctuations, gravity has less to work with. The slightly overdense regions are only barely overdense. They attract matter more slowly. It takes longer for them to grow. In fact, if Q were too small, those regions might never become dense enough to collapse into galaxies before the expansion of the universe and the effects of dark energy spread everything too thin. You'd end up with a universe that's almost perfectly smooth. A thin fog of hydrogen and helium, expanding forever, never collapsing into stars or galaxies. No structure. No complexity. No life. But what if Q were larger? Say, 10 to the power of -4 instead of 10 to the power of -5, fluctuations 10 times stronger? With stronger initial fluctuations, gravity works much faster. Overdense regions collapse quickly, violently. Instead of gradually forming galaxies over hundreds of millions of years, matter clumps together rapidly in the early universe. And here's the problem. If the fluctuations are too strong, the collapsing regions become so dense that they form black holes. Not stellar black holes, the kind formed from dying massive stars, but primordial black holes, formed directly from the collapse of overly dense regions in the early universe. If Q were large enough, the universe would be dominated by black holes. Matter would be locked away behind event horizons, inaccessible. No stars could form. The gas would be swallowed by black holes before it could ignite. No galaxies, no planets, no chemistry, no life. Or even if black holes didn't form everywhere, you'd have extreme inhomogeneity. Some regions would be incredibly dense, collapsing into massive structures early on. Other regions would be completely empty, voids with nothing in them. The universe would be lumpy on scales too large for life. Radiation from nearby dense regions would sterilize any planets that managed to form. Gravitational interactions would destabilize planetary orbits. The environment would be chaotic and hostile. So Q needs to be in a narrow range, large enough that gravity can amplify the fluctuations into galaxies over reasonable timescales, small enough that the process is gentle, allowing for smooth, stable structure formation. And our universe has Q equals 10 to the power of -5. 1 in 100,000. Perfectly tuned to create a cosmos with rich structure, galaxies, stars, planets, but without collapsing into chaos. This number, like the others, appears to be fine-tuned. There's no known law of physics that requires Q to have this value. In inflationary cosmology, Q is related to the quantum fluctuations of the field driving inflation. But what set those quantum fluctuations? Why this amplitude and not another? The fact that Q is almost, but not quite, 10 to the power of -5 tells us something interesting. If it were exactly 10 to the power of -5, we might suspect some special symmetry or mechanism forcing it to that value. But it's close, around 2 times 10 to the power of -5, depending on the scale, which suggests it's not magically fixed, but rather the result of initial conditions or dynamics we don't yet understand. What we can say for certain is that Q is written in the structure of the universe itself. Every time you look up at the night sky and see the Milky Way arcing overhead, you're seeing the descendants of those primordial fluctuations. Every galaxy is a grown-up version of a quantum fluctuation from the first moments after the Big Bang. You, personally, exist because of Q. The atoms in your body were forged in stars. Those stars formed in galaxies. Those galaxies grew from density fluctuations. If Q had been different, those fluctuations wouldn't have grown properly, galaxies wouldn't have formed, stars wouldn't have ignited, and you wouldn't be here. 5 numbers down. 1 to go. And this final number is perhaps the strangest of all. Because it's not about the contents of the universe, or its expansion, or its density. It's about the very fabric of space itself. It's about dimensions. A line. This is one spatial dimension. You can move forward or backward along it. That's all. Add another dimension and you get a plane. Now you can move forward, backward, and left-right. 2 dimensions, like the surface of a piece of paper or a screen. Add a 3rd dimension and you get the space we live in. Forward, backward, left-right, up, down. 3 dimensions. This is the world we experience every day, the world of objects with length, width, and height. But here's a question that sounds like science fiction. Why 3? Why not 2 spatial dimensions? Why not 4, or 5, or 100? This is our 6th and final number, D, the number of spatial dimensions in our universe. And the answer, 3, is not arbitrary. It turns out that 3 dimensions is special. Change D, and the universe becomes unrecognizable. In most cases, it becomes impossible for life to exist at all. Let's start by exploring what would happen with fewer dimensions. Imagine a universe with just 2 spatial dimensions, a truly flat world, like living on an infinite sheet of paper. In a 2D universe, some things would work. You could have objects, motion, even simple interactions. The 19th century novella Flatland explored this idea, imagining a society of 2D beings living in a 2D world. But there are profound problems with a 2D universe. For one thing, complexity becomes extremely difficult. In 3 dimensions, you can have networks, neural networks, for instance, where connections can cross over each other in space without intersecting. But in 2 dimensions, if you want 2 connections to cross without touching, you can't, they have to intersect. This severely limits the complexity of any structures you can build. Think about your brain. It has roughly 86 billion neurons, each connected to thousands of others. The connections weave through 3-dimensional space in incredibly complex patterns. Flatten that into 2 dimensions and it doesn't work. The wiring becomes a hopeless tangle. But there's an even more fundamental problem with a 2D universe. Gravity doesn't work the way we need it to. In 3 spatial dimensions, gravity follows an inverse square law. Double the distance, and gravity becomes 4 times weaker. This is because the force spreads out over the surface of a sphere, and the surface area of a sphere grows with the square of its radius. But in 2 dimensions, there are no spheres, only circles. The gravitational force would spread out over the circumference of a circle, which grows linearly with radius. So gravity in 2D follows an inverse first power law. Double the distance, and gravity only becomes twice as weak. This might not sound like a big deal, but it has dramatic consequences. In a 2D universe with this kind of gravity, stable orbits are impossible. Planets couldn't orbit stars in stable, long-lasting paths. They'd either spiral inward or fly away. No stable planetary systems means no stable environments for life to evolve. And there are other problems. In a 2D universe, you can't have a digestive tract that goes all the way through your body, because that would divide you into 2 separate pieces. Complex organisms as we know them couldn't exist. So 2 dimensions won't work for complex life. What about 4 dimensions? Higher dimensions sound intriguing. String theory, in fact, requires extra spatial dimensions, typically 6 or 7 beyond the 3 we experience, curled up so small we can't detect them. But here's the problem. In more than 3 spatial dimensions, physics becomes unstable in ways that are fatal for life. In 4 spatial dimensions, gravity follows an inverse cube law. Triple the distance, and gravity becomes 27 times weaker. This falloff is much faster than in 3 dimensions. With such rapid falloff, gravity becomes ineffective at large scales. Galaxies wouldn't hold together properly. Stars wouldn't form from collapsing gas clouds. Gravity wouldn't be strong enough to overcome the pressure. The universe would remain diffuse and structureless. But at small scales, with this inverse cube law, gravity becomes dangerously strong. Planets orbiting stars would have unstable orbits. Any small perturbation, a passing asteroid, a gravitational tug from another planet, would cause the orbit to spiral inward or spiral outward dramatically. In 3 dimensions, orbits are stable. Perturb a planet slightly, and its orbit becomes elliptical, but it settles into a new stable configuration. This stability is crucial. It's why Earth has been in a habitable orbit for billions of years, allowing life to evolve. In 4 or more dimensions, this orbital stability disappears. Planetary systems would be chaotic and short-lived. No planet would stay in a habitable zone long enough for life to emerge. And it's not just gravity. Electromagnetism also behaves differently in higher dimensions. In more than 3 spatial dimensions, atoms wouldn't be stable. Electrons orbiting nuclei would either spiral inward or fly away. Chemistry as we know it couldn't exist. The mathematics is clear. Stable atoms require 3 spatial dimensions. In 2D, you have the problems we discussed. In 4D or higher, electrons don't form stable orbitals. 3 is the sweet spot. There's something called the Bertrand's theorem in classical mechanics, which proves that stable, closed orbits under an inverse power law force are only possible for inverse square, 3D gravity, and linear, simple harmonic oscillator, forces. Change the dimensionality, and you lose orbital stability. So we live in 3 spatial dimensions not by accident, but because 3 is the only number of dimensions in which complex, stable structures can exist. Change D to 2, and you lose complexity and orbital stability. Change D to 4 or more, and you lose atomic stability and orbital stability. This is sometimes called the anthropic principle, the idea that the universe must have properties compatible with the existence of observers, because otherwise there would be no one to observe it. We find ourselves in a 3-dimensional universe because that's the only kind of universe that can produce beings capable of asking the question. But as with the other numbers, this doesn't explain why we have 3 dimensions. It just explains why, if intelligent life exists, it will find itself in 3 dimensions. The question, why 3, is pushed back to a deeper level. Why does our universe have the particular dimensionality it does? In string theory and related frameworks, the full dimensionality of space-time might be 10 or 11 dimensions, with all but 3 spatial dimensions, plus 1 time dimension, compactified, curled up into tiny shapes too small to detect. Why would only 3 dimensions expand to cosmic size while the others stay tiny? Nobody knows. It's another initial condition, another apparent accident that makes our existence possible. What we do know is that 3 dimensions gives us a universe rich with possibility. Enough dimensionality for complexity, for intricate structures, for networks of information, for brains and consciousness. But not so much dimensionality that physics becomes chaotic and unstable. You exist in 3 dimensions of space because 3 is the Goldilocks number. Not too few, not too many. Just right for atoms to be stable, for orbits to be stable, for complexity to emerge and flourish. 6 numbers. 6 fundamental constants woven into the fabric of reality. N, the weakness of gravity. Epsilon, the efficiency of nuclear fusion. Omega, the cosmic density. Lambda, the energy of empty space. Q, the amplitude of primordial fluctuations. And D, the dimensionality of space itself. Each one perfectly tuned. Each one necessary. Each one, if changed by even a small amount, would render the universe sterile and lifeless. So now we come to the hardest question of all. Why? Why these values? Why this universe? Why are we here? We've journeyed through the 6 numbers that define our universe. We've seen how each one occupies a narrow range of possibilities, and how deviating from that range leads to cosmic sterility. Now we need to confront the most profound question of all. What does this mean? The fine-tuning of the universe has been called many things. Evidence of design. Proof of a creator. The fingerprints of God in the machinery of creation. But it's also been called an illusion, a selection bias, or simply an unsolved problem waiting for a deeper theory. Let's explore the possibilities. Let's see where reason and evidence can take us. And let's be honest about what we don't know. The multiverse explanation. One explanation for the fine-tuning is that our universe is not alone. Perhaps there are countless other universes, each with different values for the fundamental constants. Different n's, different epsilons, different lambdas. In this multiverse picture, most universes are sterile. Their constants fall outside the narrow ranges needed for life. Stars don't form, or burn out too quickly, or never ignite. Chemistry doesn't work. Complexity never emerges. But in an infinite multiverse, or even just a very large one, eventually you get lucky. Somewhere, by pure chance, a universe appears with exactly the right constants. And in that universe, life emerges. Intelligence develops. Consciousness asks, why am I here? This is observer selection bias. We can only observe a universe that permits observers. So of course we find ourselves in a finely tuned universe. We couldn't exist in any other kind. The multiverse idea comes in different flavors. In eternal inflation, universes are constantly budding off from each other in an endless process of cosmic reproduction. Each new universe might have different physical laws, different constants, determined by random quantum fluctuations. In string theory's landscape, there might be 10 to the power of 500 different possible vacuum states, different ways the extra dimensions can curl up, each corresponding to different effective laws of physics in the resulting universe. With so many possibilities, the reasoning goes, it's not surprising that at least one universe has the right properties for life. In fact, with 10 to the power of 500 possibilities, you'd expect many life-permitting universes to exist. But the multiverse explanation has its critics. For one thing, it's untestable. We can't observe other universes, almost by definition. If they're truly separate from ours, beyond any cosmic horizon, then no experiment, no telescope, no measurement can ever detect them. Science traditionally requires testable predictions. A theory that explains everything by invoking infinite unobservable universes can feel less like physics and more like metaphysics, philosophy dressed up in scientific language. Moreover, the multiverse doesn't truly solve the problem, it just pushes it back one level. Why does a multiverse-generating mechanism exist? Why does eternal inflation happen? Why does string theory have a landscape with 10 to the power of 500 possibilities? These are new questions that need answers. And there's a philosophical concern called the Boltzmann brain problem. In an infinite multiverse, random quantum fluctuations could occasionally create conscious observers, brains, complete with false memories, existing only for a moment before dissolving back into chaos. In a truly infinite multiverse, such random observers would vastly outnumber observers like us who evolved in stable universes. If you take the multiverse idea seriously, you might conclude that you're more likely to be a random fluctuation than a real, evolved being. This conclusion is so absurd that it suggests something might be wrong with the multiverse reasoning. So the multiverse is an intriguing idea, one that naturally falls out of certain theories like inflation and string theory. But it's not a complete answer. It trades one mystery for another: the design explanation. Another explanation, perhaps the most ancient, is that the universe was designed. The constants were set deliberately by an intelligence, a creator, a designer, God. From this perspective, the fine-tuning isn't a coincidence or a selection effect. It's intentional. The universe was made for a purpose, and that purpose includes the existence of life, consciousness, beings capable of comprehending the cosmos and their place in it. This explanation has deep historical roots. For most of human history, when people looked at the apparent design in nature, the complexity of living things, the regularity of celestial motions, the suitability of Earth for life, they saw evidence of a designer. The fine-tuning of physical constants is sometimes framed as a modern version of the argument from design, the idea that the universe's suitability for life is too perfect to be accidental. And indeed, the precision we've discussed is staggering. Omega fine-tuned to 1 part in 10 to the power of 60 at the Planck time. Lambda 120 orders of magnitude smaller than theory predicts. Epsilon within 0.5% of the value needed for carbon production. These aren't rough approximations, they're exquisitely precise values. But the design explanation also has its challenges. First, it doesn't really explain anything. It just attributes the mystery to an even greater mystery. Who or what is the designer? Why did the designer choose these particular values? What constrains the designer's choices? Saying God did it might satisfy our emotional need for an answer, but it doesn't advance our scientific understanding. Science seeks natural explanations, mechanisms we can test and explore. A supernatural designer, by definition, lies outside the realm of scientific investigation. Moreover, if we invoke a designer to explain the fine-tuning of the universe, we face a logical problem. The designer itself must be at least as complex and finely tuned as the universe it created. After all, designing and creating a universe requires extraordinary knowledge and power. So we haven't eliminated the fine-tuning problem, we've just relocated it. Instead of asking, why is the universe fine-tuned? We're now asking, why is the designer fine-tuned to be capable of creating fine-tuned universes? This doesn't mean the design explanation is wrong. It means it's not a scientific explanation in the traditional sense. It's a theological or philosophical position, one that lies outside the domain of empirical testing. Many scientists who work on these problems hold religious beliefs. They see their work as uncovering the mathematical beauty and precise order that a creator built into nature. For them, science and faith are complementary ways of understanding reality. But that's a personal stance, not a scientific claim. The question, does the fine-tuning prove God exists, can't be answered by physics or cosmology. It depends on your metaphysical framework, your prior beliefs, your interpretation of what constitutes evidence. The "we don't know yet" explanation. There's a third possibility, one that scientists often prefer: we simply don't know yet. The fine-tuning might be explainable by deeper physics we haven't discovered. Maybe the fundamental constants aren't really constant. Perhaps they evolve over time, or vary from place to place in ways we haven't detected. Maybe the values we measure are actually low-energy approximations of something more fundamental. Maybe there's a deeper theory, a theory of everything, that explains why the constants must have the values they do. Perhaps in the complete equations of physics, once we understand quantum gravity and unify all the forces, we'll discover that n, epsilon, omega, lambda, q, and d are not free parameters but inevitably determined by mathematical consistency. This is the dream of theoretical physics, to find equations so compelling, so mathematically beautiful, that they could not be otherwise. Einstein famously wondered whether God had any choice in the creation of the universe. Did the laws of physics have to be what they are, or could they have been different? If we discover that the constants are not arbitrary but necessary consequences of a deeper theory, then the fine-tuning isn't mysterious, it's inevitable. The universe couldn't have been otherwise. But we're not there yet. We don't have a theory of everything. String theory is a candidate, but it's far from complete, and it predicts a vast landscape of possibilities rather than unique values for the constants. Loop quantum gravity is another approach, but it's also incomplete. And even if we found such a theory, we'd face a new question. Why that theory? Why those mathematical structures? Why is mathematics so unreasonably effective at describing physical reality? We might always face an ultimate mystery, a foundation that cannot be explained in terms of anything more fundamental. At some point, the questions have to stop. At some point, we reach the bedrock of reality, whatever that is. The implications for meaning. So where does this leave us? We've explored three main responses to the fine-tuning of the universe: the multiverse, design, and we don't know yet. Each has its merits and its difficulties. But perhaps the most important thing about the fine-tuning is not which explanation is correct, but what the mystery tells us about our place in the cosmos. We live in a universe that seems to know we're coming. The constants are set, the initial conditions are established, and 13.8 billion years later, here we are. Stardust arranged into patterns complex enough to contemplate its own existence. The materialist might say this is just luck, or selection bias, or an accident in a vast multiverse. The religious believer might see the hand of God. The physicist might suspect a deeper law we haven't yet discovered. But regardless of interpretation, the fact remains: we are here. Against odds that should have been insurmountable, we exist. You are made of atoms forged in stellar furnaces billions of years ago. The carbon in your cells was created by nuclear fusion in dying stars. The oxygen you breathe was produced by massive stars that exploded as supernovae, scattering their enriched matter across the galaxy. Every atom in your body is recycled stardust. You are not separate from the universe, you are a part of it, literally made from it. The cosmos has become aware of itself through you. And the fact that this could happen, that matter can organize itself into thinking, feeling, questioning beings, depends entirely on those 6 numbers being exactly what they are. Change n, and stars live too briefly or never form. Change epsilon, and you get no carbon or oxygen. Change omega, and the universe collapses or expands too rapidly. Change lambda, and structure never emerges or is torn apart. Change q, and galaxies don't form. Change d, and atoms and orbits become unstable. The window for existence is narrow, vanishingly narrow, and yet, impossibly, we're in it. The cosmic perspective. This is us. That pale blue, barely visible against the vastness of space. Every human who ever lived on that. Every war, every love story, every scientific discovery, every work of art, all of it happened there. Carl Sagan, when he saw this image, said, "The Earth is a very small stage in a vast cosmic arena. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe, are challenged by this point of pale light." And he's right. From a cosmic perspective, we're insignificant. The universe is 13.8 billion years old. Human civilization is 10,000 years old. Our species has existed for 300,000 years. We're barely a blip. The observable universe contains 2 trillion galaxies, each with hundreds of billions of stars. The vast majority of those stars will never be visited, never be studied, never even be named by humans. Most of the universe will remain forever beyond our reach, hidden behind cosmic horizons. And yet, we are the universe become conscious. We are matter that can think, atoms that can wonder, stardust that can ask, why? The universe spent 13.8 billion years arranging itself into a form that could understand its own existence. It created eyes to see itself, minds to comprehend itself, hearts to feel awe at its own majesty. In us, the cosmos has achieved something remarkable, self-awareness. For billions of years, stars burned, galaxies collided, planets formed, all without anyone watching. And then, on at least one small world orbiting an ordinary star in an unremarkable galaxy, life emerged. And eventually, that life looked up at the stars and understood what it was seeing. The ultimate question. So we return to where we began. Why do we exist? Why these 6 numbers? Why this universe? We don't know. We may never know. The universe might not owe us an explanation. But what we do know is this: existence itself is extraordinary. The fact that anything exists at all, space, time, matter, energy, consciousness, is the deepest mystery. And we are fortunate beyond measure to be here, now, in this brief window of cosmic time when stars still shine, when galaxies still cluster together, when life is still possible. In the far future, in perhaps 100 trillion years, the last star will flicker and die. The universe will grow cold and dark. Entropy will increase toward its maximum. Eventually, even black holes will evaporate, leaving nothing but a thin soup of particles spreading through an ever-expanding void. That is the ultimate fate of the cosmos as far as we can tell. A long, slow fade into darkness and silence. But that's not now. Now is the era of stars and galaxies, of life and consciousness, of light piercing the darkness. We exist in the brief moment between the fire of the Big Bang and the cold of heat death. We live in the golden age of the cosmos, when the universe is complex enough for consciousness but still young enough to burn bright. And perhaps that's the answer, or at least an answer worth considering. We exist because this is when existence is possible. We're here because now is the time for life, for thought, for wonder. The 6 numbers that make our existence possible are not a puzzle to be solved, but a gift to be contemplated. They are the conditions of our being, the foundation of everything we are and everything we might become. You should not exist. The universe should be empty, sterile, devoid of complexity and consciousness. The chances of a cosmos fine-tuned for life are so small as to be effectively zero. And yet, here you are, reading these words, thinking these thoughts, feeling whatever you're feeling right now, wonder, perhaps, or confusion, or skepticism, or awe. Your existence is a cosmic miracle, whether that miracle is the result of chance, or design, or necessity, or something we haven't yet conceived. The 6 numbers, n, epsilon, omega, lambda, q, and d, are not just abstract constants in physics equations. They are the recipe for reality. They are the difference between existence and non-existence, between a universe filled with light and life and one that is empty and dark. We may never fully understand why these numbers have the values they do. We may never solve the mystery of our own improbable existence. But we can appreciate it. We can stand in awe of it. We can honor it by living fully, by seeking understanding, by creating beauty, by caring for this tiny pale blue that is our home. Because here's the final truth. You are stardust that can think. You are atoms from exploded stars, arranged by billions of years of evolution into a form capable of comprehending its own origin. You are the universe's way of knowing itself. And in the vast, cold, mostly empty expanse of space, on this one small world, for this brief moment in cosmic time, you are here. Conscious. Aware. Alive. So when you look up at the night sky, remember, you're not just looking out at the universe. You're looking at your own origin story. Those stars made you. That darkness between the stars is filled with the mysterious energy that determines the cosmos's fate. Those galaxies, billions of light years away, grew from quantum fluctuations in the first moments of existence. And all of it, depends on 6 numbers being exactly right. We should not exist, but we do. And that is the greatest mystery of all. In the beginning, there were 6 numbers. And the numbers became the universe. And the universe became us. And we looked back at the numbers and asked, why? The question remains. The wonder continues. We exist. If you've made it this far, thank you. Thank you for spending an hour contemplating the deepest questions we can ask. Thank you for wondering alongside us about why anything exists at all. The mysteries we've explored tonight are not solved. They remain open questions, inviting new generations of thinkers to grapple with them. Perhaps someone watching this right now will be the one to finally explain why the constants have the values they do. Perhaps you will be the one to solve the riddle of our existence. Or perhaps the mystery will remain forever beyond our grasp, a reminder that the universe is under no obligation to make sense to us, that reality can be stranger than we imagine, that there are some questions we are not equipped to answer. But the quest for understanding, that is what makes us human. That is what makes us worthy of this improbable existence. We are the species that looks up at the stars and asks, why? And then we build telescopes, write equations, construct theories, and search for answers. We may be just atoms temporarily arranged into thinking forms. We may be here for only the briefest cosmic instant. But in that instant we choose to understand. We choose to wonder. We choose to care about truth. And that choice, that insistence on seeking meaning in a cosmos that might have none, that is perhaps the most remarkable thing of all. We should not exist. But we do. And we will not waste this gift. Keep looking up. Keep asking why. Keep wondering. The universe is waiting to be understood.